We turn to theoretically study the performance of the thresholding algorithm as an approximation of the P0 epsilon solver. The analysis we are about to present is similar to the one we covered already in the noiseless case. As before, a worst case point of view is taken in our derivations. We will assume that x0 is S sparse and its S non-zeros are located at the first elements of this vector in an ordered way. The vector b equals a times x0 plus noise vector v of epsilon bounded norm. What is the condition for the thresholding algorithm to be successful? Well, the same condition we have posed in the noiseless case applies here just as well. We should require that the minimal inner product of B with the atoms within the support is larger than the maximal inner product with atoms outside of the support. If this condition is met, then the thresholding algorithm recovers the exact x0 support. Note that this is substantially different from what we have done in the basis pursuit, where we were satisfied with a stability statement without any claim about the support recovery. As before, we will replace these two expressions by proper simplified bounds, and these will serve us for getting a clear condition for the success of the thresholding algorithm. The only difference from our previous analysis is the fact that now the noise should be taken into account. We start with the right-hand side and upper bound it. We simply plug the expression we have for B into this term. We move the absolute value into the summation and get this upper bound. Again, we encounter inner products between different atoms from A, which could be replaced by the mutual coherence. We can upper bound the inner product of the noise by the jth atom by epsilon, and this brings us to this expression, epsilon plus x max times S times mu. The last step, by the way, relied on the Cauchy-Schwarz inequality and the fact that the atoms are normalized. We turn to handle the left-hand side, and now our goal is a lower bound. This is the expression, and again B has been inserted into it. In the summation, when t equals I, the inner product becomes 1, and the term obtained is simply xi. We move this element out of the summation and proceed to a lower bound by using a reverse triangle inequality. From here on, the path is very simple, since the two elements with the minus sign should be upper bounded in order to get an overall lower bound. Thus, the term with the noise is replaced by epsilon. We are nearly done. Our next step is to move the absolute value into the summation and to replace the inner products with the upper bound, the mutual coherence. The final expression is given here, and as in the noiseless case, it involves both x mean and x max. We conclude our analysis by comparing these two bounds, requiring that the lower bound of the blue term is strictly bigger than the upper bound of the red one. We divide by x max and apply few algebraic steps, and we get to this condition for the success of the thresholding algorithm. Please observe that when epsilon is set to 0, we get our earlier result for the thresholding in the noiseless case. Here as well we see the sensitivity of the algorithm to the contrast of the non-zeros in x0. We now summarize this result. We are given a problem P0 epsilon, and we apply the thresholding algorithm for approximating its solution. We have just proven this theorem, which states that if the number of non-zeros in x0 is small enough, then this algorithm is guaranteed to perfectly recover the support of x0. This result is of very different nature compared to the one we managed to prove for the basis pursuit. Notice that in perfectly recovering the support of x0, we get an oracle performance. On the downside, however, the condition for this success is harsh for two reasons. First, it depends on the contrast of the non-zeros in x0, and secondly, this condition worsens when the signal to noise ratio, x max divided by epsilon, gets smaller.